Back. So, good afternoon. There is a time to start today. First webinar of EUXDAT. The webinar will be recorded, so there will be also a chance to see our webinar later, and the webinar will be published on our web pages to be possible for the people to learn more. I will start with a few slides of presentation at the beginning, which will introduce EUXDAT webinar series. EUXDAT is a project which is financed from European infrastructure on extreme data analytics, and now is in the last days. And today we will try to present you what we done during this project, and we have 4 webinars. The first webinar is focused on infrastructure, so our colleague who deal with infrastructure will explain you what we done. So you will have chance to learn more about EUXDAT achievements. The goal is to promote the potential, because during our project they appear these Green Deal initiatives, and we see that EUXDAT infrastructure could be good step towards Green Deal and also at destination Earth. We will be happy because we plan that the platform will stay operational after end of the project. So we are looking for partners who will be ready to test it and help us to work during the next year with the platform. For research infrastructure, this platform will be open as free. We are looking here the potential customer in commerce, so we would like to discuss with you the potential customer, potential services. And because I mentioned Green Deal, of course, for Green Deal there will be necessary to provide it a lot of research, and we are looking for potential cooperators in the area of research for the current call of Green Deal, but also for next Horizon Europe. Here you can see the programs of all webinars. The first webinar is starting now, and will be really focused on the technology. At the beginning, Javier will explain you also the relation to Green Deal, and then will come 3 pilots webinar. First will be on 22nd, which will be focused mainly on agriculture and climatic, and will be done by Meteo Blue company. The last this week will be on Friday morning, and it will be focused again on some climatic task, and will be show pilots from Czech and also from Austria. And last is next week when we will be focused on land use mapping and crop monitoring. So this is shortly about our program. You can find on our web pages, on our web pages, the links with detailed description of all webinars. I hope that Pavel will share with you all this. There is overall program, but there are also detailed program for every webinar. The last will be only published. And we will try to ask you at the beginning 2 questions and some question on the end, which can help us in some orientation. As I mentioned, we will guarantee 1 year free testing for research purposes. If you will need more contacts, then please contact me or some from our colleague who will present it, and you will see the contacts. Pavel, can you now publish the first questions?
Sure. I put into the chat the link for the voting for the Mentimeter together with the code, and I will share my screen for you with the voting, so you can use either the link or just the code for the Mentimeter. So feel free to tell us what type of organization you are working for at the moment. So I will give you like 20, 30 seconds to fill in. And after that, we will put the second question into the table.
Well, seems that till now, no industry, no research.
There is one research, Karel.
No research, yes, not industry, nor SME. Sorry.
Well, do we need more time to fill in the first question? Or do we move to the second one?
I think that we can move to second.
Okay, then. This is the question about from whom you learned about the EUXDAT project. Social media or another sources or from your colleagues, friends, or family, or was it another source of information?
I think last question also 7 people answer.
Okay, so that's it. So
Okay.
as we see, the best way how to share information is the mouth words. Thank you
Okay,
for voting.
so, and Javi, now I would like ask you to take presentation and tell us about the relation of EUXDAT and Green Deal.
Okay, I'm turning on my camera. You can see me now?
Yes,
Yes.
we see you.
Yes.
Okay.
So probably we will need also if you will share your screen.
Yeah, I'm doing it. Okay, share the screen. Okay. So, can you see my screen?
Yes. Okay.
Perfect.
So floor is yours.
Thank you, Karel. Okay, well, I'm Francisco Javier Nieto. I'm the coordinator of the EUXDAT project. And well, as you know, we are finalizing our project, and this is a good opportunity to get in touch with the stakeholders. So what I'm going to do is to give you some introductory talk about the project itself, what it does, and how it's related to the new initiatives, European initiatives like Green Deal and Destination Earth. So I will go through the objectives, and I will tell you also about things that we do in the project and what we offer as a project. And then I will tell a few words about the European Green Deal and the Destination Earth initiatives, and how what we do in EUXDAT is possible, is mapping to the different concepts that are included in these initiatives. In the end, I will just give you a summary of what EUXDAT could do to implement these two initiatives. So first of all, about the EUXDAT context. So we are today in an environment in which we have many data sources. So we have meteorology stations, taking data about the temperature, humidity, precipitation, even the composition of the soil. We have also satellite images. I guess you know the Copernicus system, all the Sentinel system that is collecting information from the Earth. We also have drones. In some cases, they are mounted with hyperspectral cameras or multispectral cameras, which are taking also images closer to the ground, not like satellites. Also, there is machinery today that is collecting a lot of data about the behavior of the vehicles. We have other data sources like the Open Land Use Map, which tells you, and the cadastral information, which is providing information about the different areas, how they are used in the land, and so on. And of course, we have meteorology, climate, and forecasts, and all these kind of things. So, and yeah, of course, there are other information like hydrology systems and all these things. So there are many data sources that could be used in order to support a better, let's say, or a different way to do agriculture, let's say. That is the reason because we defined 3 main pilots, which have to do with land monitoring, sustainability, energy efficiency when using the land and when managing the crops, and 3D farming. These are divided in several scenarios in which we do some specific, we address specific problems in which EUXDAT basically is in the middle, gathering, collecting all the information, implementing some algorithms, and managing all the resources that you need to compute all these things in the background. Okay. So basically, EUXDAT is the enabler, so it will be possible to implement these kind of scenarios and pilots. Just to be more focused, EUXDAT was born as a project for large data analytics as a service infrastructure. These infrastructures basically have to provide the means for researchers and other stakeholders in general in order to be able to build new scenarios and solve problems which have to do with sustainability and proactive agriculture. In that sense, basically, in the project what we were aiming at doing was managing data storage and movement. We had very big and large data sets, so we had to support also very heterogeneous data sources coming from different places, different data formats, and we also needed to somehow be able to configure the policies of managing these data as well. On the other hand, when it comes to processing and to dealing with all of these things, one of the things we wanted to include is not only cloud computing, but also HPC, which means that some adaptations were necessary. And also, as this is very complex technology, and usually we want researchers to be more focused on solving the agriculture problems, the idea was to provide some advanced features through a user's portal. Of course, as an infrastructure, in the end, the purpose is to provide some services that can be accessed by stakeholders and to implement some pilots so you can see the utility and really access something that is useful for agriculture domain. And of course, to facilitate a long-term sustainability and collaboration. Here, I mentioned some resources infrastructures that are important. Actually, we'll see more about the EOSC in later slides. But PRAISE is the one related to HPC. EOSC is related to cloud for research infrastructures. Just as an example, what we wanted to do with EUXDAT was to really go a step farther of the typical scenario that we may have. So in general, if you want to delimit agroclimatic zones, you can take information from the meteorological providers. Meteorolog, for example, is one of those that we have in the project. You can take this information and see more or less what is the weather forecast expected in your area. But the point is that usually you won't have enough resolution for small fields, which are the ones that in which the farmers need to work out. So in this example, we were combining several data sources in order to get much more accurate models with respect to frost dates and the temperature and the weather you may have in a concrete area. So you see the difference between the original model, and in the end the third one would be what happens when we have combined all this information and we have processed all the data. So I think that there's an important difference there. We have prepared an infrastructure in which we are collecting several tools together. We have data catalogs, we have a marketplace, we have development notebooks online. We have a lot of libraries which are devoted to agriculture. We have visualization tools. We have also tools for specific for moving the data, for managing the resources which are in the background, for monitoring what's going on. So there is a large complexity behind this that will be explained later by in the next talks after mine. Okay, but what can we offer as an infrastructure in general from the high level perspective? First of all, you can manage and do an analysis of large data sets. Okay, you can go to our infrastructure and create your own application. So you have an idea, you have the notebooks, and you have the data connectors. So you can connect to the different data sources, download the data, and use the specific libraries that we have for implementing your algorithms. And moreover, later on, you can also use the visualization tools in order to visualize the results that you have generated. On the other hand, it provides the mechanisms for easily access HPC and cloud resources. You can use, for example, only HPC, only cloud, or a combination of both. In the end, the point is to abstract the complexity of these systems to the end users, so they don't need to take care of how these systems will work. And it's important to mention that what we can offer as well is access to several scenarios we have already implemented. If I'm not wrong, right now we had 6 and maybe we'll have 7 at the end of the project. We have also multiple example in the notebooks. So we have examples on how to access certain data, how to use certain libraries, how to visualize certain results that you may get with different formats. So you have examples of all of these things that you can reuse for yourself. Okay, and then standardized APIs thanks to this usage of connectors. So you can use one concrete client to access the information that you need. Now, the European Green Deal, just to give a brief introduction, in case there is still somebody who doesn't know. Well, the Green Deal was born as in line with the United Nations 2030 agenda, in which they saw that as they are worried about this thing of the climate change, and they see that we need to somehow do things in a different way. So basically, Europe defined a strategy in order to improve the well-being of citizens and to protect the environment in general. Okay, so they defined 4 main objectives in this initiative, which were, first of all, become climate neutral by 2050, which goes beyond the objectives of 2030. They want to reduce the pollution because they want to protect the environment and also the people. They need and they see that they need to support companies and the industry in general to become clean, and while still they're leaders in their markets. And they want to support an inclusive transition focused on the citizens themselves, what they need, the workers. I mean, what the workers need, the regions. I mean, more focused on the individuals rather than on like a generic idea or strategy. But this requires, first of all, major changes in key sectors of the industry: energy, transport because of mobility, the industry in general, how we do the buildings, and how they behave, and all these things. So because they see that a lot of or most of the issues related to climate change are related to these sectors. But also it's they understand that they need to, it's necessary to do very important investments because I mean, this is going to cost a lot of money if we want to get there, you know. So somehow it's necessary to support that transition. So how to implement this? So first of all, Europe is proposing a new European climate law in order to support all these ideas, all this strategy. And on the other hand, they are going to provide some financial support in this transition, green and digital, what they call the green and digital transition. So, I mean, become more clear and more clean and become more digital. Plus, this, as you all know, with this COVID-19 issue that is challenging all the world, actually, they have seen this program as also a possibility, an opportunity for boosting the recovery of Europe. In order to do so, they already defined some key work streams, as you can see in the next slide. It's very much in line with what I said before. So they understand that, or they want to do this important transformation in the economy. So these are the 8 key areas they identified: increasing the use climate ambition, supply clean, affordable, and secure energy, because in the end, these are 75% or something like this of the problems came from the energy generation. So they want to do a decarbonization strategy. Mobilizing industry for a clean and circular economy. This is important for sustainability. Building and renovating energy and resource efficient way. Accelerating the shift to maintenance smart mobility. The farm to fork idea. Preserve and restore, especially restore ecosystems and biodiversity, and the zero pollution ambition. Okay. And you see in blue the 2 main actions which can be done. From one side, they finance the transition, and on the other hand, they want to put the mechanisms just to not to leave anyone behind. And basically, in all this strategy, it's easy to see that already EUXDAT could be very in line with this farm to fork concept, okay, because it's totally in line with agriculture, and actually it's mentioned that the friendly food system EUXDAT supports that. As you may already know, they have launched a new call for proposals as part of this financial strategy. One of the things that they did was to define a new work program to support Green Deal with 1 billion euros of new research projects that will support all these things. And they have identified like 10 main areas, yes, and there are several subtopics inside each area. According to what we have seen, we believe that EUXDAT will be very in line with the 6 and 7 areas from to fork and the biodiversity and ecosystems. We will be supporting the strategy towards these 2 main points, but also EUXDAT could be useful in other areas. For example, the part of preventing and fighting extreme wildfires, because it's possible to use EUXDAT for supporting landscape planning related to the kind of crops could be in different areas, and also to the zero pollution solutions related to the use of chemicals, fertilizers, things like this. And in the last 2, there is a part related to research infrastructures for supporting Green Deal challenges, and the products and services which are related to support this climate adaptation. Okay. In those areas, we believe EUXDAT is an enabler and can support the development of new technologies. Then Destination Earth, this is another initiative which is pretty much in line with Green Deal. Actually, they see Destination Earth as an initiative to implement partially the Green Deal. Well, not partially, it's a kind of key initiative for implementing the Green Deal. So its high-level objective is basically to implement European strategies. Green Deal is one of them. Digital Age, I mean, they have several strategies in which the Destination Earth has a role. In the end, the point is to maximize the socioeconomic benefits of all of these strategies and enable the modeling of very complex systems. So basically, they need to deal with climate change, sustainability in circular economies. And there is one important book, which is Security and Sovereignty, which has to do with, there is a very global competition in technologies. And in some cases, we forget that we depend heavily on technologies from third countries, so Europe has realized that this could be an issue. So at some point, if Chinese are controlling certain hardware manufacturing or software production that you are going to use, and at some point, because of a conflict or whatever, they decide to close the access to technology, then you will have really real issues to growth and to maintain the situations that you had. So sovereignty is very important, and this is one of the one of these new key ideas that the European Commission needs to take care of. So in the end, Destination Earth is a proposition for a European solution to do complex models, to solve mathematics which are behind these models, and in the end to really support or to really implement these decision support tools that will support all the strategy towards Green Deal. Okay, how we can do this? Well, the point is to bring together some key technology areas that have to do, first of all, with the resources provision. European Open Science Cloud as a cloud solution, plus HPC, because we are going to need a lot of computation and to use a lot of resources in general for storage, computation, whatever. Another point is European data spaces or large data in general. Usually they highlight the part of, the Copernicus system and the DIAS platforms, but there are many more data sources, as we already know in EUXDAT. Another pillar here is artificial intelligence. We are doing a lot of progress in general in the IT research towards new tools based on artificial intelligence and more complex models. And finally, connectivity, which in the case of Europe will come from GIANT. Okay, it's very important that we have very good internet connections, so we can really move the data from here and there in an efficient way. So here in this picture, you can see how they relate the different technologies to concrete initiatives that are already ongoing, EuroHPC for HPC, European Open Science Cloud for the cloud part, GIANT connectivity, as I mentioned before. So what we see here is that the EUXDAT would contribute. Okay, first of all, in HPC and cloud part, because we provide access to resources in an abstract way, a transparent way to researchers. Also from the part of big data, in terms that we provide a lot of connectors that can be used and the tools for moving the data. And also we support artificial intelligence. We have a few scenarios in which, for example, machine learning models are used, so in the end, this is something that we can support actually, because also libraries for doing implementing sources based on artificial intelligence are available in the platform. Taking a closer look, you see that they defined this digital continuum, in which you see that you start from physical systems, in which, you could have your field or wherever, in which in the end you have sensors that are collecting information about what's going on in that environment. These myriad of sensors are managed by the Internet of Things solutions that collect all the information and move the information and store or even filter what is necessary, or they can do even some data fusion, which is related to that big data part that is in green. And Then, with all of that information that we have, we can perform some data analytics, cognitive computing, okay? In the end, we need to extract knowledge from that. And that is computed and stored in HPC and cloud infrastructures, okay? That is the reason, because you have this circle in which everything's all the time, you are rolling all the time there. And as before, can EUXDAT support this initiative? Yes. So, as I said before, we can support a part of big data, we can support a part of data analytics, we can support a part of HPC and cloud. Right now, we don't support a part of, I mean, even if we are able to connect to some IoT solutions, we are not providing ourselves an Internet of Things platform, okay? We access to whatever is available. On the other hand, in the picture of the left, you can see a kind of more complex kind of architecture that they defined, in which we believe that the EUXDAT could support a part of applications and middleware. Okay, we have access to hardware, but I mean, the important HPC centers or big clouds, or the EOSC, for example, we are not part of the European Open Science Cloud, but we can access the resources that the European Open Science Cloud is providing, okay, to researchers. And just a summary, so I close my talk. So how EUXDAT can be mapped to these strategies from the European Commission? Well, from the strategic perspective, Green Deal, we have already scenarios which are supporting precision farm, which is related to this farm to fork idea. Therefore, of course, we can support this idea of sustainable food, that concrete area that they didn't identified, that can support improvement in agriculture methods. Of course, we can also use EUXDAT in order to define solutions for landscape planning, forestry, things like this, and even to improve how certain materials are used, for example, fertilizers, which can be quite toxic depending on how you use them. On the other hand, from the technical perspective, which is what we see as the other part of Destination Earth, we already provide connectors to multiple data sources and heterogeneous, actually. So we have connectors for climate information, satellite information, even drones, as I said, to information, for example, of IoT coming from one of the partners, which is Castel. We already provide also mechanisms for large data moving and processing, thanks to the different libraries which are available in our platform. You can access HPC and cloud resources in a transparent way, I would say. So you don't need to really take care of the technical complexity. We also did some parallelization of codes. We will see later some example, because this is not trivial, okay? Using cloud, okay, it's you can run pretty much everything in cloud, any simple application. But if you want to use HPC and you want to really exploit the full potential, you need to do some adaptations on parallelization. And this is something that in a few cases we have done already in EUXDAT. So it's something we have experience with. And finally, and something which is, I think, very interesting is that it's possible to access development and testing tools for stakeholders, so you can create your own applications, test whatever we have, and I mean, in general, really even use scenarios that we have already implemented. Okay, and that's all from my side. Any question?
Thank you, Javier, for this very interesting presentation. If there is some question to Javier, or you can also write your questions to the chat all time continuously, and we will then transfer these questions to the people, or you can ask now if there is some question now. If not, I would like thanks one more time to you, Javier. And now I think we will move to Anna or Fabien.
Yes, hello. I will share my screen. Can you see my screen?
Yes.
Okay, thank you. So I will do a presentation about the end users platform. First of all, it corresponds to what Javier has presented, an overview of EUXDAT project. EUXDAT is not a standalone application or service. It relies on a hosting infrastructure based on cloud and HPC, and it uses a set of external data sources, meteorological data, in situ sensor data, UAV data, soil maps, hydrology, climate data, and Copernicus data coming from Dias Mundi, which is also the provider for the cloud in current version of the platform. In EUXDAT, with all these data sources and the infrastructure, the features available for the users is to access these data sources, to prototype a new application using these data sources and processing large data from these different sources, to run an application on a cloud environment or HPC environment, also to publish an application, and to access value-added products from other applications. We have two types of users. I would say standard user to browse the available elements, and also developers of solution, because EUXDAT allows to, in fact, prototype, develop, integrate, and publish value-added applications in the domain of agriculture, relying on powerful hybrid infrastructure for the execution, in fact, and relying on a set of external data sources to start from and to enrich or to combine. So let's have a look at these different profiles of users. All users can browse what is available on EUXDAT and launch the demonstrator applications already developed within the frame of the project. Developers of solution can access a prototyping environment hosted on the platform with an access to the different data sets, either directly or through APIs or libraries. To access also a set of pre-configured geoprocessing libraries in order to simplify the access to these libraries for all users, and also access a lot of examples of usage, documentation on the connectors, on the libraries, and eventually examples from other users. The developers of solution can access the powerful hybrid cloud HPC environment for the execution, and can also deploy and publish their application, their service, library, products in EUXDAT. In terms of components, on the user interface of EUXDAT, I will show you a demo just after, but I will try to present the different components a little before. So we have a main page, a web page presenting the access to all the other components. We have demonstrators, which will be presented in the pilot sessions after this one and for the next two sessions of the webinars. We have a catalog to browse the available data sets, the possibility to develop a service with a prototyping environment based on Jupyter notebooks and configured with geoprocessing libraries and data connectors. We can access, a user can access his private data within a dedicated private workspace. The marketplace allows to publish the service and to browse the available services. And there is also a monitoring component to access the resource consumption on the platform, on the components and the scenarios also, in order to monitor the platform activity. So when a new user wants to publish an application, today we will look at the platform with this point of view of a new developer of service. So first, of course, you need to have an idea of a value-added application. Then it's necessary to identify the data sets to use. So within EUXDAT, it means browsing the catalog to see what is already available on the platform. To identify the needed libraries. So here it will be more a browsing of the documentation to see what libraries are already configured. You can upload your own data if we talk about private data. You can add your own libraries if we talk about private libraries, but otherwise it can also be a request to the EUXDAT operator to add missing libraries and connectors in order for them to be available for all future users. And once the connectors and libraries are available, you can start to prototype your application online with Jupyter notebooks in EUXDAT platform. This allows you to run Python algorithms, to visualize the results. And once this prototyping is sufficient for a first version, this version can be integrated into the platform for an execution on cloud or HPC infrastructure. This is done with an orchestrator mechanism in EUXDAT. There is the next session I will present you with a little more details the orchestrator mechanisms. So on the execution environment, the algorithm can be run, but it's not a user-oriented launcher yet. So if you want to have this algorithm available for end users, you need to develop also a launcher, either a user interface or a REST API, for example, or package it as a Python library. In that case, the content starting from the notebook can be sufficient. So this launcher needs also to be integrated into the platform. And then you can validate, iterate, and finalize the creation of this algorithm. In order to publish it, you need to define the terms of conditions, billing rules to publish into the marketplace in order to have this new application available for external users. If you have questions, do not hesitate to ask on the chat or directly. In terms of data, we have a large set of data connectors available on EUXDAT. Some data sets are stored on the platform. Others are external to the platform and are accessed through APIs or libraries. We have the access to Copernicus data from Dias Mundi. the access to climate data store from Copernicus also, the European Digital Elevation Model, open land use data sets and map, the land parcel identification system. We have historical weather data from MeteoBlue services, soil condition sensors from PESEL instrument services, soil maps datasets that are stored, a subset of the soil map datasets that are stored on the platform, access to hyperspectral data from UAV, from CERT, hydrology, and all OpenStreetMap datasets, and also the possibility to upload private data into the user private workspace through the next cloud component I will show you just after. So we have quite a large set of connectors. They have different kind of interfaces, and we present for each connector a set of examples of usage in order to show how to integrate them into a new algorithm. There is a geospatial metadata catalog. It's based on OpenMika component. This catalog contains the list of datasets, services, and applications available on the platform in order to browse what is already accessible. As I said, the prototyping environment is based on Jupyter technology. So it's notebooks for integrated geospatial data analysis. So it's an open source component with a lot of programming languages. Within EUXDAT, we are using mostly Python. So this one is configured. It could be extended for specific purposes. It's a widely used tool, which allows to, at the same time, have the code, the documentation of the code, and the visualization of the results. And there is, here it's quite large, a list of libraries already configured with a set of geoprocessing libraries, Sentinel Hub and EOLearn libraries, for example, to access the Sentinel images, GDAL, we have GRASS also, P geoprocessing, we have Orfeo Toolbox, which is more configured as a tool, and some utility libraries to access images, graphs, and large data, also data frames like pandas. And as we are based on the Python environment, all the powerful Python libraries for machine learning can, of course, be used in the different algorithms. An online documentation is available within the web portal in order to document the different components and to provide hyperlinks to the different examples of usage. So examples for data connector access and for all the geoprocessing libraries. I said that users can also upload their own data from a tool named Nextcloud. In fact, both Jupyter tool and Nextcloud access the same user private workspace in order to upload private data, to access the content of the data, for example, the results of the algorithms, and to download it locally. Also to share content with internal or external users of the platform. I will show you that also in the demo. So here is an overview of the architecture of the platform, more a detailed view. I have presented these different components: the main page, marketplace, catalog, the different demonstrators already available, the notebook, prototyping environment, the private workspace, and the monitoring component. All of this is the user interface of backend services that are all compliant with microservice architecture, with all services packaged as Docker containers and deployed on a cloud infrastructure using Kubernetes. We have also some databases or distributed file system for the different data used. And with a larger view, these components are deployed on top of a platform as a service layer using Kubernetes technology, so an orchestrator for Docker containers and deployment on a scalable cloud infrastructure. So the platform as a service layer on top of the cloud infrastructure, we also have an HPC infrastructure. And here the development environment is more for project developers to have the different version control system and automated deployment pipelines to redeploy the different components of the platform. That was just to show an overview of the architecture behind EUXDAT. I can show you a demo of the web platform. So EUXDAT is available on test.euxdat.eu. When you connect to this main page, you have two tabs, one with EUXDAT scenarios. These scenarios will be presented in the pilot sessions. So for now, we have 5 demonstrators of applications developed with EUXDAT. You see for each of them a description, a list of data sources that are used, corresponding to the ones I presented before from the different connectors available. And when we explore one of the applications, we are asked to log in. You can register as a new user and you access the application with its description. I won't present you this application because that's not the purpose today. Sorry, I come back to this one. I will present you the catalog and the prototyping environment and private workspace I have talked about just before. So if you want to browse what data sets are available within EUXDAT, you go to the catalog. You can see that there are applications, services, that there are, data sets, applications, services, different kind of elements available. You can filter. If I want to have a look at Sentinel data, for example, Sentinel-2 data sets, I have a description of these data sets, of the provider, and I can also go to the resource locator. Here I am redirected to Mundi Web Services to also browse their own catalog of data and see which products are available on a specific area, on a specific time frame. So if I have a detailed view of the product, I can have all the characteristics, and it can also allow to check if we have products for a specific date, for a specific location, with a user-oriented catalog of data. Sorry, I come back to OpenMika. So here we have this for all this kind of products. Let's have a look at the prototyping environment. I will go directly through the online documentation. I'm already signed in, so it remembers me. So the prototyping environment is a Jupyter environment. You have notebooks like this one open. You have a browser of the different files and folders. All the elements I highlighted in blue are common to all users, and you have a private workspace directory with your personal files. In the public folders, you have common examples, and you have also the documentation, which is here. We will browse a little the documentation to see what is available in terms of example. So you can find documentation on the prototyping environment, how to start working with Jupyter notebooks if you are not familiar with it, which instance to start, how to copy, what are the libraries available within the notebook. Some documentation about the data connectors. For example, how to access Sentinel data. So accessing Sentinel data from Mundi within EUXDAT can be done with a REST API, and you have the description of the REST API here. You can use a Python library from Mundi, and you can use also Sentinel Hub. We can have a look at one of the examples here to use WMS OGC standard, so web map service to display a dedicated Sentinel product on a map, cropped on a rectangle for a specific date. I will just clear all the outputs. So here is a notebook. If you are not familiar with it, it's composed of different cells. Some of the cells are executable, so Python code, and some are text. So you can run cell by cell. Here, I just import the libraries from Mundi. And basically, I access a Mundi catalog with the Sentinel-2 collection. And I get a WMS endpoint. So the OGC WMS standard allows to obtain a map from coordinates, date for an area of interest, time of interest, and specific output format characteristics. So I get the characteristics of the endpoints, the description, the textual description of the endpoints, the list of operations available on this endpoint, and also the list of layers available there. You have all the raw bands of Sentinel-2 products, B1 to B12 and B8A. And you also have some band combinations already provided by Mundi. So natural colors, for example. For each layer, we have more detailed characteristics. Here's just, again, description of operations. And here we will call the get map operation. So we will call it on a B box, a rectangle with these coordinates for one date, the 21st of April 2018, with this projection and a resolution for the final image. And we will get it as a PNG image just here to simplify the display on the notebook. So we do that for each of the layers here. So for the row bands, but also for all the layer combinations. And we get one image per layer available. Here it was the area of Toulouse in France 2 years ago, a little more than that. And you can also go further. You have examples of different file formats, etc. I won't go into more details for this one, but you can have very detailed examples for the access to WMS layer here and other endpoints offered by Mundi. For EUXDAT purposes, in general, we don't use rectangles. We are working with polygons. And we can use row bands, but it's much easier to work with indices computed as combinations of other bands. So in that case, we are working with also Sentinel Hub libraries if we want to have a WMS endpoint. This Python libraries provided by Synergize is, I just import standard elements here, allows to do the same easily with polygons and band combination. Here we define a polygon, quite a complex polygon. We get just the B box around this polygon because it's necessary for the operation. Some documentation about how to write the coordinate systems here. We use the same data source. So we start from the same list of available layers on the WMS endpoint. But we will try to combine them this time. We can use a time interval or just one date. Sorry, I forgot to clean. I'm here. We define that we don't want images with a cloud coverage over 20% because we don't see anything. And here is our request. Here we use a predefined layer, but we just say that we request this layer with a polygon. The result is really cropped on a polygon area. We will do the same, but this time, instead of using a predefined layer, we write ourselves the script to express the band combination. So here we combine row bands 8 and 5 from Sentinel images. And we can pass this script as a parameter of the request. So we get it for the geometry and with this script. we get the same result because the script corresponds to this exact band, but starting again from row bands. And there is a third possibility a little after here. You can also take the script from an external URL for more complex scripts or already published ones. It's a good way to do it. So that's basically Sentinel Hub library usage, but showing within EUXDAT examples of use, integrating it, and starting from this kind of detailed examples really gains a lot of time to start a new algorithm definition. That was some examples of Sentinel data access. I can show you another example with the digital elevation model. We host on EUXDAT some datasets from digital elevation model over Europe. We have developed a REST API on top of that to access it. So here are the operation of this REST API to get subsets, in fact, of the digital elevation model on a specific area from a projection to another projection. And here I have another notebook example to show you that. So we will use these coordinates. Output and input projections are the same, and we just call the get subset operation, so which corresponds to the Python version of this operation. The red is normal, it's just logs. I'm waiting for this cell to be run. I get a TIFF file, in fact, and I just save it. I transform it as a PNG just to show you the result. So in my private workspace, I have this PNG file corresponding to the TIFF image resulting. Okay. And then that is done. And then we can display this image over a map in order to show the digital elevation model over this map. So it's also a good way to start to visualize the different elements from the prototype, from very early in the development process of a new algorithm. The last example I wanted to show was maybe access to external services like MeteoBlue services. You have MeteoBlue APIs provided, and you can make requests to this REST APIs and get. Sorry, I have to run it again. So you indicate coordinates. There are several parameters for this historical weather data requests. And here is one example where you get the, I think it's the monthly average of temperature on a specific location. So you can also get the numeric values of all your results and start to display them on a map in order to start to think also about the future user interface of this service. Sorry, so I showed you the catalog and the prototyping environment. Let's have a look also at the private workspace access tool, which is Nextcloud. In fact, it's a file sharing standard tool. But what we see here corresponds exactly to the content of our work directory from Jupyter environment. So I can have a look again at this PNG file, term subset dem, .png, it's here. I have the same file. I have the different folders. I can move it easily, and I can also share it with other users. Oh, sorry, I had done it already. So if I want to share it with other users, I can share directly with other EUXDAT users in order to, for example, if we work on a same team on the development of a new application, it's really interesting to be able to share such files with colleagues, or to show the results also internally or externally. I can, if I want to share it with Karel, I think, or to with Pavel maybe, yes, I can add him, and he will see, in fact, the file like this, with a indicating that it comes from another user, but it's very easy to also work in collaborative mode with these files. You can upload private data here. So for private data sets, for example, it's a really easy way to do it, and it can be read from the Jupyter notebooks, but also from the package services packaged into Docker containers and deployed on the platform. In terms of demonstration, I think it's all I wanted to show you. And you will have a deeper look on the orchestrator monitoring mechanisms and parallel computing in the next sessions, and another more feature-oriented look on the different demonstrators available on the pilot sessions.
Thanks, Anna. It was very nice and very good presentation, and I think that it gave a very good overview of EUXDAT platform. Is there any question from the people? Maybe I will stress two things, very important, that all solution was done on the combination of open sources. It is one, and other things is Anna can confirm that we now tested to migrated the platform on other cloud, and we are able to demonstrate that this is really possible to migrate the solution on different clouds, that it is not connected with one platform.
Yes, I can confirm, Karel. We are quite close to the to the final migration of all the components on another cloud hosted by Wireless Info. And this kind of infrastructure based on Kubernetes and Docker with a major use of standards, both in terms of technologies, interfaces and deployments, really helps to redeploy a new platform again, and to have everything deployed and working quite easily.
Okay. So if there are no questions, I think that the next speaker will be Jesus, yes?
Yes, good afternoon.
So please put your camera and your screen.
Okay, let me set up the camera. And I think you can see my screen. And we'll start.
Yes, we can see. Yes, you are now in presentation mode. Okay,
Okay.
so your floor is yours.
Okay, thanks. Well, this presentation will be conducted by myself or by my colleague, Paolo Marangio. Both are working in ATOS HPC, Advanced Parallel Computing Lab here in Madrid. We are going to discuss, comment about some components that we have been developing, extending, and setting up in the context of EUXDAT project. In particular, the orchestrator, monitoring, SLA manager, and accounting, who in some sense they are working together, they are collaborating. And then Paolo will complete this presentation with some words about the parallelization work he did for one of those, the EUXDAT use cases, and how the throughput of this use case has been improved by applying parallelization techniques in HPC infrastructures. So starting from the EUXDAT platform introduced by Anne in the previous presentation, we are going to focus on very few components that are working in the backend of the project, particularly orchestrator, monitoring, and some related components like the accounting and SLA manager, who are not included in this picture. In particular, the orchestrator is seeding workflows in different hybrid infrastructure, including cloud and HPC, which main statistics are computed by monitoring, which is collecting this data about the current execution of those workflows. And this data could be used by the SLA manager to detect whether the quality of service is being guaranteed or there are violations in these quality of service contracts. And also can be some of this data collected by accounting in order to charge by users by the use of these resources. So this information can be relevant for the accounting or financial department in the infrastructure provider. So we will focus on all these components. I will start with orchestrator. The orchestrator in EUXDAT is based on Cloudify, but concretely, we have been working in a plugin for Cloudify, which is an orchestrator for HPC workflows for the composition of batch applications or job-based applications in the context of HPC. So this plugin has been developed in the context of Cloudify, because Cloudify is one of the most popular workflow-based web server orchestrators for cloud. So that consists of a huge number of plugins that you can use in order to deploy your application to the cloud. This component has been set up in the context of EUXDAT. And we have gone beyond by supporting as well, which is not supported already in the Cloudify orchestrator, in order to support the orchestration of HPC infrastructures. Croupier is working as a meta orchestrator in the sense that it's delegating in the low-level orchestrators and schedulers in HPC and in cloud, like Kubernetes or the Slurm, in order to actually deploy and execute different workflow tasks. So in that sense, the combination of Croupier and Cloudify supports the execution of pure HPC cloud hybrid orchestrations. The application model that is being used in order to describe the application deployment topologies is based on Tosca, which is a standard which is very popular in the realm of cloud, which describe the application workflows in terms of Santos YAML files, which are describing the different tasks and the dependencies between those tasks. So we have extended this topology, the definition, in order to support as well HPC applications. So we can combine different plugins in order to support the hybrid deployment within cloud and within HPC. And in the context of EUXDAT, we have been also supporting the transfer between cloud and HPC in order to transfer data from cloud to HPC when jobs are requiring data that is in the user host by using GriffFTP and by using the data transfer component developed by HLRS. Similarly, we are also supporting reporting to monitoring job statistics in jobs executed in HPC, and to report to accounting the resources that has been consumed and could be charged to the end users. From the user's perspective, users can interact with this component by using a command line interface and also the graphical user interface provided by Cloudify. So in terms of architecture, I want just to highlight here that the Cloudify is able to interact with the HPC infrastructure through a common interface that manages different schedulers supported by the different HPC, target HPC infrastructure that the workflow may target. And also we are supporting the data mover component that migrates data from the HPC and the cloud environment by using GriffFTP. In terms of user interface, the main user interface is Cloudify. The main concept in Cloudify is that you can deploy your workflows that are called blueprints in this Cloudify terminology, which describe your workflow, and then you can deploy this workflow as many times as you like by providing different inputs. So the same workflow fed by different inputs constitutes a deployment, and the execution could be completely different because the inputs are completely different as well. So through the interface, you can see the visual description of your workflow. Here we have a very simple workflow consisting of 2 tasks that are executed in parallel in the HPC infrastructure. Then you can also inspect your inputs. You can also support the execution of the different actions related with the workflow. You can install it, you can run the different jobs. And also you can see all the logs provided by the Cloudify orchestrator when running the workflow. So you can see what is being executed and what were the results. So this is a brief description of the orchestrator. And now Paolo is going to introduce monitoring.
Hello, everybody. Can you hear me?
Yes.
Yes, great. Okay, so thank you for the introduction, Jose. So I will take over with the monitoring component. So as the job is being executed by Cloudify or Croupier in detail, Croupier actually collects some information about the execution of that job. And that is what is the monitoring component essentially interested in. The monitoring component for the EUXDAT project is based on 2 well-known software that are available open source. These are Prometheus and Grafana. Prometheus is essentially like a database that collects, scrapes, and saves information about, again, these metrics. And Grafana is used for showcasing these metrics in a user-friendly way. For the EUXDAT project, we are essentially monitoring 2 types of metrics that are related to cloud execution and metrics that are related to HPC execution. So for example, by using Prometheus exporters, we can directly scrape information about different metrics that are relevant to our Kubernetes cluster. So for example, memory usage of a specific pod, CPU usage, again, of a specific pod, but also cluster memory usage and pod replication controller. These are just some examples. With regards to HPC, then Prometheus can also collect HPC information that is manually pushed by orchestrator. So for example, the length for the job execution, the CPU time, and the memory consumed by a specific job. So in the next slide, there is a visual representation of the different components I just described. So we have Prometheus in the middle, which is represented by a server that has a connected persistent volume for storing the data. But on the left, we have the actual data, which is, in this case, Kubernetes pods information, as well as nodes and cluster information. These are scraped by the Prometheus server. And then this script information becomes data source for the Grafana tool, which allows to monitor the performance of your jobs and your applications. So in the next slide, there are two dashboards that are within our Grafana component. So on the left, we have CPU usage for all the components. Well, for some components that are running inside our Kubernetes cluster. And on the right, we have the memory usage for the same components. As you can see, we can measure essentially the evolution of these metrics over time at every second as the job is being executed. So I guess in the next slide, we can also see the last type of another dashboard essentially that shows you these cloud-related metrics. These are cluster-related metrics mostly. So for example, we can easily see how many containers are running in our cluster, how many of them are being terminated or restarted. Also some general health metrics about the cluster pod usage, and so on. This is all very intuitive and user-friendly, as you can see here. So yeah, we can move on to the SLA manager. So now that we have these tools that allow you to essentially automatically monitor all this information, then the next step is to essentially place some standards of quality on these metrics. And this is the task of the SLA manager that monitors these metrics on the fly and checks whether they meet certain standards that are set out in a service level agreement or SLA. So this is based on a REST interface that allows to create and update agreements. Then whenever there is an evaluation that leads to a violation, basically when this agreement is not met, then there is a violation. And this is then leads to an action, which is configurable and essentially, for example, could be applying a discount, which is done by the accounting component, for example. So I think that's all I have to say about the, oh no, sorry, there is one more slide just to show you how an agreement looks like. So this is a JSON file that contains different fields where, for example, the user can define the name of the agreement, but also the provider and the client that are relevant for a specific SLA. And finally, in the guarantee section, we can, for example, put a certain threshold of an operation metric against which we are evaluating that metric. So that is how the SLA manager essentially works, by creating these agreements that are evaluated against these monitor metrics, and then eventually the action mechanism is represented, well, if achieved by making a request to the accounting component, ideally.
Okay, thanks, Paolo. Another component is accounting. Accounting is the service we have created from scratch in this project in order to collect all the consumptions of chargeable resources consumed by workflows in both cloud and HPC by different users. So the main idea behind is to collect the consumed resources per workflow that could be notified either by standard reporters, like for instance, orchestrator, or that we can pull in a scheduled way from statistics from the monitoring service. So for reporting, we have a number of APIs that are available in order to report what are the providers that we are accounting for, what are the infrastructures that they are providing, what are the resources, sorry, the users that are consuming the resources, and what are the reporters, for instance, the different components within the infrastructure. For the different resource types, we can also define the fees for amounts of consumption and the optional discounts that could be notified from SLA manager. And then we can collect all the consumption that has been reported for different workflows. For querying, we have as well a complete API in order to provide individual consumptions, I mean fine-grained consumptions per provider, infrastructure, resource type, users within a time frame or any combination. And also we can report the accumulated or average consumption for the same criteria defined above. Accounting graphical user interface is being developed in the context of the EUXDAT portal, from where developers, from where users and administrators can collect all this data and report this data to the finance or accounting department. In terms of architecture, in terms of interactions, the accounting is being fed by different sources of information. One is the orchestrator. The orchestrator can collect data about the resources that has been consumed in HPC for the orchestrations and jobs that has been submitted to the HPC. But also although it has not been implemented yet, I mean, the marketplace can also report about the services that have been consumed, or for instance, other data providers could provide the same kind of accounting information. The SLA is using the accounting API in order to notify discounts when there are detected violations in the SLA agreement. And the portal, the user interface for accounting, is also using this accounting API in order to interact with component, pull data, and also to register providers, infrastructures, resources, accountable resources, and so on. There's another mechanisms to collect data from the monitoring by pulling the data from monitoring, the data that is describing the use of resources in the current infrastructure and also in the HPC infrastructure. This is an example of API. This is a complete API, which is being exported in the web and can be used by any user or by any client, which offers CRUD operations for the different classes, domain, records that are collected by accounting. And this is an example of the user interface that is being now developed. It's under development, in which, for instance, the user can collect a list of resources that has been consumed by the workflows that has been submitted by this user in concrete infrastructure. For instance, here we are selecting one of those possible infrastructure that we are using for testing in EUXDAT. This is for another project from Soda Live, but it's an HPC infrastructure provided by HLRS. And here we are collecting all the records in all the time frame. I mean, the historical records. We can also restrict the query to a very concrete time frame. So this is completely the overview of the different components that we wanted to present today in this session. And now Paolo is going to explain the use of parallel technology in HPC in order to improve the performance of the pilot for our climate zone scenario. Please, Paolo.
Yes, thank you very much, Joseph, for the introduction again. So now, as Joseph said, we're going to talk about parallelization. So for the ones that maybe were not so knowledgeable, Parallelization essentially means applying multiple processors to a single computational problem. To make this more concrete, a computational problem can be an EUXDAT application, for example, the agroclimatics zone scenario. And what is this scenario actually doing? Basically, it's a demonstrator that allows users to calculate a time and spatial distribution of an agroclimatic factor called the frost dates that is relevant and influential for the length of vegetation period. And this is computed based on the historical data from the ERA 5 land dataset. And actually, I will not say too much more. And there is another session on this topic by Wireless Info on October 23rd. In this diagram, sorry, in this picture at the bottom of the slide, you have a picture of the Czech Republic. You can see the data, the spatial resolution, and you also see this orange grid. And I drew this grid just to essentially make you realize how we are framing this problem, computationally speaking, when we are executing it on HPC, and also compare that to the serial execution. So let's say that we want to compute this factor for this area delimited by this bounding box, which has these 4 coordinates shown by these yellow pins. Then we can discretize this area of space using, well, into 2D, essentially in a 2D grid that has 16 columns and 16 rows. This is not really what you see in the diagram, but I didn't really manage a way to draw 16 columns very quickly. So just to show you that you can discretize this into grids. So let's say that you have 16 by 16. And then that means that you have 256 areas for which you can compute, well, little rectangles essentially, for which you can compute this, this parameter of interest. So in the next slide, I will then describe how we approach this parallelization of this algorithm. So basically, the scenario can be broken down into, let's say, 3 different functions that are nested inside each other. So the first one is the find frost dates function that computes information for a single year and rectangle that I just showed you, also known as grid point. And within the, this function is nested within another function called frost dates yearly. Now that function computes information across multiple years. Finally, this function is nested inside another function called frost dates places. And this function computes information across multiple grid points. So the idea that we had was parallelizing over the outermost function, this frost dates places, by scheduling the execution of this function across multiple processors using MPI. So that through this parallelization, one MPI process would be responsible for 1 grid point. And then that grid point could be also computed over several years. So if you go back to the previous slide, I don't know if there's an easy way. Oh, well, it's okay. Yeah, so thank you. So basically, the idea is that each of these rectangles will be computed by a different MPI process. Compared that to the serial execution, then all of these rectangles will be done by 1 process. So this is the idea that we had. So if you go 2 slides ahead now. Okay, so now that we have parallelized our code, then we need to execute this code through HPC. In order to do this, we need to create a blueprint that is can be executed through Cloudify that was described by Yosu. So then this blueprint is submitted through the orchestrator. I'm just reusing this graph that was shown already by Yosu. And then again, this blueprint is executed on HPC by orchestrator. And then we can, for example, collect information about that job using the monitoring component. Also, we can collect information through the accounting component relevant for that component. And finally, we can also evaluate the metrics from the monitoring component using the SLA manager. So this is just to show you the relationship between this, the execution of this scenario and how the other components are leveraged to allow this to happen on HPC, essentially. Can we go on the next slide? Thank you. So this is an excerpt of the blueprint that we generated in order to run this scenario on HPC. I will not really go into too much detail because that would be like a different webinar on this topic. But the thing about Clarify and Croupier is that you are able to configure easily the interface against which you are executing your job. So you see in the node interface, HPC interface, you have a lot of there is a way for you to specify the credentials and the configuration of the interface and the entry point, for example. And if you go lower, then you will see that you can easily configure commands that can be run on HPC. So we can ask the HPC to execute the job using, for example, MPI run. And then we can move that output file from the HPC to the cloud, or well, first to the workspace on HPC and then to the cloud, so that it can be parsed there by the front end. And also here you can also see below commands in benchmark job, you can see that we can select the number of nodes, we can select the type of nodes, the number of MPI processors we want to use for this execution, the wall time, and so on. So this is all configurable from our interface. And the user doesn't have to explicitly log in onto the HPC infrastructure. So if you go to the next slide, this is just to show you the results that we have gathered from the execution of this particular scenario on the HPC, and in particular on the Hawk system provided by HLRS in Stuttgart. So what do we see here? We have two plots. The first one is showing you execution time recorded over increasing number of MPI processors. And in the bottom, you have this speed up. So basically, here we have two lines because we were testing for execution of two different problem sizes. So you have the full line, which is for 256 grid points, essentially, that I show you like in my initial slide, if you remember that orange grid. So imagine that you are computing for that exact grid, which has 256 pairs. And then you have a smaller one, which has 64 pairs. And we can see that as you increase the number of MPI processors, there is a linear decrease in execution time. So if you try to run that entire grid of points, which was for like a specific area of Czech Republic, it will take you on one on one MPI processor, so like on one CPU, let's say, over 32,000 seconds. That's roughly 8 hours. Now, if you run that same simulation, well, that same computation on 256 pairs, so on the bottom right of the top diagram, you see that the execution time now is, let's say, around 150 seconds. That means that you've taken something from 8 hours to 2 minutes. So that really shows you the power of HPC, like in at the full by mapping one MPI process to one grid point. So there's a one-to-one mapping here. So each of the MPI processors we are using are responsible for a different rectangle in that grid. And that's really the maximum you can achieve with this kind of problem size. Then as you increase to 512 MPI processors, then you see that there is no more improvement. And you have the same trend with the other line, which is the dotted line, for which we have a smaller problem size. Again, linear improvement until you have the maximum improvement when there is a one-to-one mapping. And now the last thing I wanted to tell you is speed up. Speed up is just another way to show the same information above. And it tells us that when you're running with this one-to-one mapping, and if you look at the column for 256 processors, you reach the maximum speed up that is more than 128 times. So that means that when you run your code with 256 MPI processors, then that's 128 times faster than if you run that same code with one MPI processor. So again, massive improvement by running this with the HPC. So that's all I had to say on the parallelization. I hope it was understandable. I don't know if you have any questions. Otherwise, actually, there is more information on parallelization provided by the collaborator, Jose from HLRS in the next session.
Okay.
Thank you so much, Paolo. And this is concluding this session. So I will be very glad to answer questions you may have. Thank you so much.
Thank you.
Is there any question? If not, I would like to ask to Jose to go to the last technical presentation for today.
Hello. Oh.
Hi.
Hi. My camera is fixed on the keyboard down, then you have to see soon down. Okay. Let's see here. Okay, you can see my slides, right?
Yes, yes, we see you can start. Thank you.
Okay, the idea is make an introduction about parallelization of code in Python with MPI. Then I make an index. First, I'm going to make an introduction why is intended to do here in this presentation, and later I will make examples with code and results on all the different kind of primitives on communication with MPI and Python. Then first, the situation currently, the geoprocessing applications are increasing the amount of data they can use. They increase the amount of processing also because the amount of data is increased, and the requirements of visualization also increases. Then the kind of problems they are going to solve in geoprocessing are these challenges are requiring more and more computation time, and we are going to target to use the parallelization tools for reduce this computation time. The main applications in the market now are MPI and OpenMP. And then let's continue. What is parallelization computing? Okay, I think it was already a good example from Paolo in the previous session. Anyway, my original idea was to show this. This is like a laundry. You want to wash a lot of clothes. You just can distribute between the different machines. And this means these machines are working independently. One can start do this job, and when finish, not meaning what is doing, and the others are already busy, already finished or not. But this is not happening when we are going to do physics simulation. We want to distribute a load between different computation nodes. Let's see, this video is not about farming, looks similar. I look in Google about farming simulation, I got this. Sorry. PowerPoint die. Let's see. I have to set the screen. Here. Sorry, my PowerPoint crash. You can see, right? Okay. I think it's not like I watch the video when it's running.
Oh, we don't see.
Yes, you can see.
No.
Oh my God. Okay, let's see how I do. Okay. I missed to press. Let's see, not crash again.
Yeah, okay, now it's okay.
Okay, the idea is there is some kind of physical scenario here, and they are going to simulate the airflow here. It is this wind farm, but we can think in like a trees or some other thing. Then wait a few seconds, we are going to see the airflow. And the airflow is moving here, and we can see the physical simulation. The point is, to make this kind of simulation, the air, the volume, is divided in cubes. And each cube, like here, is allocated in a different computing node, like Paolo saw in the previous session. Then the problem is, each of these cubes, we are running in parallel. We are simulating in parallel what is going to happen with this wind here. And each cube have to interact with the other cubes. Like there are some pressure between this volume of air and this other volume of air. There is some transfer of material or transfer of heat and so on. That means each computing node is simulating a different cube, but they need to communicate between them. And this is the point of MPI and OpenMP, providing a solution for this. Then OpenMP is only for running on a single node, because they can share information then run memory. MPI allow also to run on not only in single computing node. You can run in the cloud on HPC because this MPI includes a library for communication. Then we are going to have multiple nodes running and computing something, and this MPI will make a solution for us how to share this information between them. Then we are going to see next on this presentation about different communication library primitives here on MPI. And I'm going to put examples of them to make it easy to see how they are working. The Python-MPI in particular is, you are still using the same MPI you're using on other computing language. Yes, Python-MPI, it's what it's doing is making like an interface to use this. Yeah, we consider to use Python because it's the main trend currently on geoprocessing applications, and also because multiple pilots in EUXDAT also implemented in Python. Then the basics is we are going to run some amount of processes on, with Python-MPI. In this example, I will try to put always small numbers, like in this case, there are only four processes. Then the code is simple like this. Each process will just write hello and the process number X from a total amount of something. To run this kind of code, you can just run MPI run, number of processes you want to use, Python, and the script of Python. You can put additional parameters like a file. In this case, I level like a machine file. This file can contain a list of machines with like IP addresses where they can connect. You can provide the same names on the command line, or yeah, on this. Next, when I run this, MPI I just mentioned is the number of processes. We are going to have 4 processes, and the result will look in the screen is like I am the process 0, 1, 2, 3, or 4, 0, 1, 2, 3 from a total of 4 processing process running. Here I put laptop is the name of my machine, but we put multiple nodes where I can see on which node is running each one of the processes. This is contained here in the name, it's the processor name, and rank is which is your position in the list, and the size is the total amount of processes. Then now going to see the different primitives, what is the most interesting on this, because it's almost everything. If we run 2 parallel processes, we can send data from one process to another one. Then the function is like sending and receiving. It's not the best option because these functions are blocking. That means, and the second and the third number, process number 1 here will stop working, waiting for the data. There are other alternatives we are going to see in this presentation. Then one function, one application will send and the other will receive. In this case, I'm going to use on all the other slides this kind of way to illustrate how it's working. The processes are here, like 0, 1, 2, 3, and 4. And the data is, we can send multiple iteration of data, we can put in a different column. Then the process number 0 is sending a value A, and the process number 1 is going to receive this value. I try to explain here the same information. Process 0 sent to the process 1, this red cube is on some data. The code again is very simple. All the header is the same like the previous one. In this case, if I am the process number 0, I'm going to send this data, and I specify the destination. If I am the node, the process number 1, then I will receive. I said from which node I'm receiving this information. Then I can print on the screen. This function allowed like each process can send different messages to different destinations. We can add additional field here like a tag. We can put a label to each message. In the case we are sending messages from 1 to 0, and we not wish the messages are confused between them, then we can add a label like is the message number 1 or the message number 2. And here is I'm waiting for some kind of message. Then again, the same command line I reuse, just change the name of the script, and MP run, and we can see the first process sending this data, then the second process said I received. Now we are going to do similar process, but one point is in this case is many processes are sending information to a single one. This is in this case I choose the process number 0. And I'm going to add a second function called to the MPI is like a barrier. I wish in this case to all the process stop here and then continue together starting from the same point. Notice this function is interesting on few particular cases, not always you try to use it because blocking some process to keep running is a wasting of time and resources. And we have to look in this particular application, what is the most interesting for you. Then here I'm going to use comp-reduce. In this case, I'm going to make an addition of all the values. Then each one of the processes send a different value. The process number 0 will collect all the values and make an addition of them. Here in the bottom, I try to represent this. Each one is sending a different value, then I place like a color box in a different color. And the box number 0 will make the addition. We can see the code, the header is the same. Here I put a function for generating some random of vector of numbers. And here is the code. Each one is going to send the data to the first one, and we make a here comp-reduce. Comp-reduce will take the local sum from each one of the different processing elements, and will collect the total, the addition of all these values in the global sum. Here we specify the function. That what we want to make the addition is MPI sum. We can use another kind of mathematical operations to combine all the results. In this case, if there are the process number 0, then I print the result on the screen. And you can see each one of the process print the values they generated randomly, and finally the process number 0 is printing the addition of all these values. Then here I just put a list of different mathematical functions, like what is the maximum, the minimum, or we have different alternatives to, depending on your case, you can use. I'm quite fast. I will finish too early. Anyway, next, the broadcast function is like we are going to send the same value to every other single process. Okay. Then the first process is sending to all the other 5. You can see the same box. Same box. I want to mention now, take chance, and then I will make an example with both. We can send these functions with and without the buffer. Buffer, that means we can have a memory prepared to collect these results and store in some kind of memory. Then when the process reaches that point, can use these values because are already collected. In this way, it seems the code is working faster. But we need to provide additional information like how many elements we want to store in the buffer and which kind of type of data is placed there. Here I place integer. I think it's in the example I put a float. Then the first one on the left is without the buffer. I just generate a data is this structure and is sending to all the nodes receive the same information as we can see below. And on the right side, I place like an array of floats. And then, sorry, I just put all to value 5 or something like this. Then another function, another couple of functions, and again, I'm sorry, I didn't mention the difference to choose when your buffer is the first letter. It's lowercase, it's not buffer, it's capital case, it means the function is going to work with a buffer. And this extends for every other function we are going to see in the presentation. Then scatter and gather means we have one node, not necessarily have to be the process 0, can be any other process. The one process have data and want to distribute this data among all the other processing elements. Then in this case, I put like there are different color boxes and each other node can get one of these pieces of data. And gather is similarly, but in the opposite process. We want the first node have this data, but it's not like previous when we talk about reduce. We are not going to make a mathematical operation of it among them. We just want to get the vector with all these values. Then gather, what we're going to send is all of them send the data back to the one particular processing element. In this case is you specify in the function you said that here I put the processing element 0. Here I make a couple of examples. All the examples here on the presentation are really tested. Looks very short, but they are really working. And I put the outputs on every single time I put the code down. And then what I'm going to mention here, we can see in the first one, we have a sequence of values. I think every node is receiving, let's see, scatter, yeah. It's receiving the square of 1, square of 2, square of 3, the function is here. And the other is, the values distributed, and finally, each node is send all this 1, 4, 16, 9 is received on the rank 0. One thing I also mention is you can see the things not seems here sorted like 2, 3, 0, 1 is not in sorted. The idea is this happens if you run this code in your computer, you will see every time you execute in a different order because the process running in parallel, you have not guarantee which one will finish first. Then another one is all gather. In this point is all the processing elements will share information with every other one. It's like the gather we see before, but we want like each processing element have a copy of all the results. Then here is very short example and produce like this. All the nodes receive the same vector of numbers. I almost finished my presentation. 3 more slides. Sorry if I'm too fast. Then all to all is very similar. You see columns and rows are split here. That means the process elements send the vector A, and each one of the processing elements will get one of these elements of this vector A, and the other will get in sequence. Then I provide an example. I already tested. This is working perfectly. And we can see I put some random string of values and they get, the first column, you see the zeros are here, are right here. The process element 0 send 0, 1, 2, 3. And we can see the first place of each vector arriving to destination is 0, 0, 1, 2, and 3. You see the process elements are not sorted. Then next point is the typical question is, let me find one of these figures. This is okay. What if we want to distribute values from 0, but we not wish to distribute to all the processing elements we have in the system? I mean, if we are making a huge simulation, like at the beginning, then one cube have only 6 neckbones, up, down, left, right, front, and back, but we not wish to send the values to hundreds of processing elements who they are not our neckbones and they don't care what the value we are going to send. And when we can select a range of destination elements to send the information. Then if you see in the previous, in the examples, we are always working on this community of elements we call like com here. We get the size, the rank, and so on. And using com gather or com scatter, this com is defining this community of processing elements we are going to be target of this transfer. Then what we are going to do here is, if the system have four processing elements, and we want to divide them split them in 2 different separated groups, we will still have defined the full system. We can still send in, okay, I want to send a message to the full system. All the processing elements will get the data. If we split, in this case, we can say, okay, I want to send only to the blue processing elements or only to the green processing elements. Then in this case, we can define, this is at the beginning, the header is the same before. We have like a community of processing elements, like all are working together. Then for half of them, I'm going to say like your color is 55 or your color is 77. Then in this case, we generate a new rank, a new size on this new community, depending on the color. This is MPI wall split. Depending on the color, we get a different. In this case, just simply I print on the screen. I am a processing element on the full system, and the processing, for instance, we can see already the result. I am the processing element 0 from a total of 4, or 2, 3, or 1 from a total element of 4. In the second part, I didn't print the color. If I rewrite this, I will put the color. The first two we can see they maybe are on the same color. We use one processing element 0 and 1 from a total of 2 processing elements, and the same happen on the second part. Then I think this is all the most important. Now, if you want to use this kind of functions, you have to understand how to distribute your load between the processing elements. What Paolo did when they distribute between those 256 processing elements, you have to understand the problem. You have to understand because you will try to make the load equally balanced between them. If you have one node doing 99% of the work and the other doing almost nothing, you will not get big improvement on the execution time. The idea is the biggest improvement in execution time is when you can really distribute the load between all your processing elements. Then and this need understanding your problem and need understanding also your data to be able to know which data have to be distributed everywhere. And one more additional improvement is when you run one single processing, for instance, if your application is sequential, maybe you have to store a lot of data in your RAM memory. When you have not enough RAM memory, the data have to be loaded from the hard disk. And the hard disk can be 100, even more than 100 times more slower than the RAM. And they have big impact on the performance. The point is, when you distribute your data between all the processing elements, the amount of RAM memory you have is larger. In the supercomputer, you have different computing nodes. Each one have its own RAM memory. That means if you don't need to read from the hard disk, you can access all the data already stored in the RAM memory. You can have big impact, a big improvement in the performance of your application. Then it's not only about considering how you divide your code, it's also about how to distribute your data. Then I think this is the most important. Somebody have any question, maybe?
Okay, thank you, Jose, for this very nice presentation. If there are no questions, so in such case we will start to ask you for some answer. Pavel, if you can share your screen.
Of course, I'm about to, so give me a moment. I'm sharing my screen, and there we go. There is the, yeah. This is the next question to answer.
Yeah, okay.
Good, good.
So do we wait until we have 7 votes, or?
Could
Okay. We are getting close. So if we have the 7th one, we would have the same amount as before.
Yeah, maybe somebody left the channel, I don't know.
Yeah. Okay,
Yeah.
I think we can move on. Yeah, we got 7. 8, okay. And we are running.
Okay.
Okay, let's move on. Yeah, what? Give me a sec. There we go. Next one. Do you think that EUXDAT can help to implement the destination Europe? And we have 7, so we can move on to the next question.
Okay.
Okay. I would like to, yeah, there we go. And we have here the priorities of Green Deal. And which one do you see that EUXDAT can be the most relevant one? I think you can check more than one option.
Yeah, it looks so that there is possibility to put more.
Okay, no more voting. We got 7. Cool. So we are done with this question. So let's move to the another one. And yeah, it's a pretty simple one. According to the webinar, we would like to know whether you are interested to test the infrastructure. And we are happy that you are. And we are getting, yeah, to the next question, which is what would be the purpose of EUXDAT infrastructure to use for?
There is again possible of multiple answer, yeah?
Yeah, I was about to say that. And now we have 8 answers. Okay, and we are getting closer to the end of the Mentimeter voting. And that's the question about if you see Green Deal as relevant for some priority in next Green Deal call. Oh, there should be EUXDAT, not Green Deal. Sorry. And now we have a different kind of a question. Do you see EUXDAT as relevant for some priority? Yeah, for the area, for the areas of the next Green Deal call. You can slide all of these options, let's say.
Jak teda vlastně my po tom roce zhodnotíme, že má právo na to dostat nějaký ten koupit z nás ten podíl. Nevím, asi je to něco, co bychom si měli taky spolovat společně, anebo teda už to bude něco, čeho teda má jedna ten příce, jakým třeba návrhem jako vám přednést. To nevím, tam do toho rozhodnutí spadá, ale vlastně to se mi napadlo, kdybychom si o tom povídali, protože to, že něco prodá, sice zní dobře, ale myslím, že se bude dobře poměřovat, myslím si, když na něco, na nějaký kontakt nás jenom přivede, něco bude jednak víc. No.
And we will wait a couple more seconds, probably for the 7th one. Yeah, there we go. Thank you for the voting. And yeah, this is the final question, I believe. Will you be interested to join our consortium in the next Green Deal call? Okay, and I believe this is all for the voting. And we thank you very much for your contribution.
So, I would like to thanks to all who participate today. Pavel, can you share the link on Thursday program?
The link for the program.
Or maybe you can share the screen with the program on the EUXDAT's webpage to see. The Thursday, it will be focused on the presentation of Meteo Blue. You heard about integration of Meteo Blue data today, and Thursday will be a big presentation of Meteo Blue modeling of, it will be modeling of climate risk analysis and prediction. So we will be happy to hear or to meet you on Thursday. The next will be Friday morning, where will be 2 pilot presentation, agroclimatic zones and field accessibility tool. One will be done by Wireless Info team and second PESEL, and last presentation will run on next Monday. So we have a full week. I will be very happy to meet you again in the next days. And I hope that this presentation was interesting for you. I expect it so because many people stay till the end. So thank you very much one more time to all presenters, and thank you for your patience to stay here this long afternoon. So goodbye.
Thank you very much. Goodbye.
Goodbye. Thank you. Bye-bye.
Goodbye.